When we go out to infinity this way, it goes down forever to negative infinity. And if we try and go this way, we can only approach 0 from the right, and this time it goes up to infinity. Yes? Did I say, what did I say? I think I said negative, didn't I? I apologize. I did say that. My mistake, my mistake. Thank you for catching that. If A is bigger than 1, it looks like the red one. If A is less than 1, it is the blue one. Less than 1 and still positive. All right. Properties of logs. Logarithmic functions are also continuous, at least on their domains. We already said you can't plug negatives or 0 into logs. So as long as you're looking to the right of 0 on the x-axis, then that graph of that logarithm should be able to be drawn without picking up your pencil. And then we have these properties from college algebra that you may or may not remember that were really, really convenient. We're going to use these a lot, all right? The first property says that if you have a single logarithm and inside of it you have multiplication, you can turn it into 2 logarithms with the x here, here, and the y here, and you turn it into addition. So a single log with multiplication inside turns into 2 logs with addition. Yes?
How did we find out these rules? Like, why are they addition?
It actually, you can prove it using the inverse of that, which would be the exponential function. I can try and show it. You want to see? All right, so let me do it this way. Let me get some board space since you're asking. All right, so let's say we have, let me make sure you understand this first. If I take a to the log base a of x, that's equal to x. So we have to at least agree with this first, that if you take a and raise it to the inverse function, the logarithm, that it basically they kill each other off and you just get x. Similarly, if you take the logarithm base a and inside of that logarithm you put a to the x, that you get x. Those two things we have to agree on. Do you agree with that? Right, that's the whole property of what inverse functions do. They kill each other off. So the question I'm being asked is, why is log base a of x times y? Why is that equal to log base a of x plus log base a of y, right? Like, why is that true? Well, what I could do is I could start by looking at what is a to the x plus y? That's a to the x, right? Times a to the y. Do we buy that? Yes? Okay, what would log base a of x be over here? Or sorry, what would log base a of this be? So if I take log base a on this side of the equation, what would I get over here? X plus y, right? And then over here, what would happen if I take log base a of a to the x times a to the y? Well, you can't use the property we're trying to show, right? Right? This right here, we can't split it into 2, can we? Can you though? This is multiplication, right? This is multiplication. So what can I do? Anyone see what I can do or no? How? I'm not sure I understand. I just want to make sure I understand. Say again? You mean put these together and then get a to the x plus y? If we do that, what's going to happen? I think we're going to wind up back where we were, right? If you put those together, what happens? You'll get this is log base a of, you're saying change that to a to the x plus y? I think that's what you're saying. And then these will kill each other off now, right? And then you just get what here? X plus y equals x plus y, which is true, but we haven't proven anything, have we? Right? We haven't proven anything. We've just shown that x plus y equals x plus y. So, all right, so we're here, right? We're here. What can we do? Is there anything we can do? What would happen if you did, look at where we're trying to get to, okay? Look where we're trying to get to. We're trying to get to this, right? From this. So trying to use this statement right here, I put this here first because I think most of us agree with that, right? That's the one thing for sure we do know. So working from that, does it look like we get anywhere? Taking log on this side, taking log on this side. Does it look like we get anywhere? No? I'm trying to see if I can lead y'all through this or not. Do y'all want to? Are we getting anywhere is what I'm asking you. Do you feel like we're any better off now than we were before?
Yeah, we're closer.
We're closer to this?
Wouldn't the proof just be that when you multiply two exponents together, you get that?
Yes, but how does this tell us that this is true? That's the question. Can we start with this, which we are all agreeing is true? Can we start with this and get to that? That's what I was trying to do, to see if it made sense that if we took log on both sides, yes, this side turns into x plus y, but what's this, right? Through here, can't. Because that's what this would be, right? If we distribute here to here, that would be that. But we're trying to show that it's addition, not multiplication. This is a good problem, actually. I'm wondering if I should actually prove it or not, because I think this is a really good exercise. I know, but this is one of those things where if you just do it, you do it, and it's done, and there's no like critical thinking about it. Why don't we do this? Can we table it and come back? Is that okay? Just because I want people to actually don't just go to Google and be like, try to look it up, all right? See if there's a way that you can start with something you know and draw that conclusion. But at no point in time can you ever use that because you're trying to prove that, all right? So can you start with something you know and turn it into that? Or can you start with maybe the right-hand side, you know? Can you start with that and somehow turn it into that? And you can't just make up your own rules like, yeah, that comes together and this is what I get. You can't make up your rules. The most you could do is somehow convert this into maybe its exponential form. So I'm gonna let y'all, whoever wants to play with that, play with that. I would offer it as a bonus, but it's too easy to go find the answer, and then everyone will turn it in, and just because they went and researched it. So.
I wonder if you could convert it to exponential terms, you were saying the other part, you want A to be.
This one?
Yeah.
Yeah, and maybe something happens.
Yeah.
Okay. See what you get. I think that's a good exercise. Yeah, I don't want to get us because if we go too far off on this, we'll just go down the rabbit hole. I was already about to go down a rabbit hole with this anyway, so.
I want to know now.
You want to know? Well,
Can you just
too
stop?
bad. Yes, I can. I can stop. It's no problem. I can just keep going. Look, you accepted these in college algebra, right?
Yeah.
Yeah, you accepted them in college algebra. So this is the other rule. You have a log of division becomes subtraction, and then this is the big one. This one right here. Now this one I can prove to you easily, but you basically have to agree that that's true. So these two look familiar?
Yes.
Okay, this one is the one we need the most. And it says that if you have log base A of something to a power, that power can come out front. And there's a simple way to prove this one. If I write x to the r, that's x times x times x, and I do that, that's r times that I'm multiplying them. And so every time you have multiplication, it becomes addition according to this, right? So you're just going to have log base, this will be log base a of x plus log base a of x plus log base a of x. And then how many of them will I have? Whatever r is, right? So if I have r of those together being added, then I have r of those logs, right? There's r of those logs, right? If I have 10 apples together, that's 10 apples. So really, this power in here just comes out. Okay, maybe I'll do it at the end of class. We'll see. I don't know. I still want people to think about it. All right, those three properties are extremely important. All right, there were some special exponential and log functions that you learned. Two of them in particular, but the first one was called the natural exponential function, and that's when we let that base be e, right? And I already told you all, I gave it away earlier this semester, that function is very special because it's the only function that does something specifically with its derivative. You remember me talking about that? No, it was that the slope of the tangent line was just the y value. It's its own derivative, all right? Now, I don't want to get more, we'll talk more about that in just a second, but that was a very special one. So do we all agree that this is just, e is just, what, approximately 2.718? So it's a positive number, right? And so when we graph e to the x, it should do that, right? That's what it should do. And then the inverse of that function, the inverse of e to the x, is log base e of x. That's the inverse function of that one. But that's not the way we write it. We write it like this instead. And that's just because, I mean, historically, it's because this function is so important in science and math, chemistry, biology. This function comes up so much that we needed to be using its inverse a lot. And back in the day of typewriters, subscripting on a typewriter sucks because you type, then you'd have to like turn the drum, hit the key, turn it back, continue typing. And if you were writing a paper, a research paper, and you had to put this logarithm in there like 500 times, it would slow you down. So we just agreed that anytime you want to do log base e, just do ln, this is L, not I. ln, it's French, logarithm natural, okay? Logarithm natural of x. So yeah, that's the way the French do it. If it was English, we'd be like natural log, so it'd be NL, right? But because French, they do the logarithm natural. So that's what that is. That is the natural log. Y'all have seen the natural log. I know you have. All right, here's some properties specifically of the natural log and the e function. Of course, when you put them together, natural log composed with the e, they kill each other off and you just get x. Or if you do it the other way around, e to the natural log of x, they kill each other off, you just get x. We should all be familiar with the fact that e to the 0 is 1 because any number to the 0 is 1. Well, any non-zero number to the 0 is 1. And then this one is the backwards fact, right? If I plug 1 into the natural log, it should spit out the 0 that went into the e. So that's just the reverse. Everyone here should be comfortable with those. And then natural log of e is 1. That's another. This is actually the first one. Yeah, that's that first property. Imagine that the x was a 1. If that x was a 1, then the answer would be 1, right? Well, that's what's happening here. That's e raised to the first power, so the answer is the power. And then finally, we have this really nice thing called the change of base formula. Most of you are aware of the fact that your calculators only have 2 keys on them. Most calculators have either this key or this key. Most calculators have both of them, right? There's only 2 keys on the calculator. And the reason why you only need 2 keys on the calculator, in fact, you only need 1. You don't even need this one. is because of this change of base formula. You can take any logarithm of any base of any value, and you can just use your calculator and do natural log of x over natural log of a, and it'll give you the answer. So that is a very nice, convenient thing that we use to solve logarithms with our calculators. All right, I do want to go down a small rabbit hole. So I just said right now that f of x equals e to the x is the natural exponential function, right? The inverse of that function, the function that undoes that one, is the natural log function, right? The natural log function undoes that one. And you can say it the other way around. The e undoes the natural log. Then there was this other one, okay? This other function over here that I'm not going to say what it is, but its inverse is that other key that most calculators have, log of x. Who knows what the base of this log is? 10. It's base 10. So this is actually, if f of x is 10 to the x, then if you say log of x, the base is 10. Now, this one is important to us because of the properties of calculus that I told you about, how the slope of the tangent line, like this is the only function, right? This is the only function that turns out to be its own derivative, all right? So this is a really important function to us. And that's what the next section is going to be about, is like why is the derivative of that itself? But this function over here, there's a key on most calculators for this base 10. The question is, why is this one so important to us? Why is the base 10 exponential function important? Why not the base 4 exponential function? Why not the base 8 exponential function? Why not the base 15 exponential function? Why is this one important? You gotta, what do you think?
Is it because our number system is a tens?
Yeah, our number system is base 10. Now, do you know what that means? That's why I want to go down this rabbit hole. Do you know what it means that our number system is base 10? I'm about to see. I'm going to take you back to grade school. All right, if I give you a 3-digit number, let's say I give you 345, okay? We all understand that if this was money, that would be like me handing you 3 hundreds, right? 4 tens, and 5 ones, right? So this digit right here is how many hundreds we have, right? This is how many tens we have, and this is how many ones we have. What I want you to see is that each of these numbers here, 100, 10, and 1, right, are just powers of 10, right? This is 10 squared. This is 10 to the first power, and 1 is 10 to the 0 power, right? So each digit represents how many, so this 5 means I have 5 10 to the zeros. This is 4 10 to the ones, and this is 3 10 to the seconds, right? If I add another digit, 7, this is how many thousands we have, which is how many 10 to the thirds we have, right? 1,000 is 10 to the third power, right? And every digit I go on, right? Now, what about backwards? If I put a decimal point here and now start going this way, right, like this, if I put, let's say, 6 here, and then let's go 2 here, and let's go 1 here. Well, what's the pattern? What should the next one be? 10 cubed, 10 squared, 10 to the first, 10 to the 0, 10 to the negative 1. Well, what does 10 to the negative 1 mean? 1/10, right? 1 over 10. This is how many tenths you have. What would the next one be? 10 to the negative 2. That would be 1 over 10 squared is 100, right? That's how many hundredths you have. Next one would be how many thousandths, right? Okay. Now, I'm almost done, not quite. So when we look at our number system, right, if I were to give you the opportunity to give me a 3-digit number right now, how many different numbers could I put in here? How many options do I have? I have 10 options. What are they? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? I have 10 options. So I only get to choose from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are 10 options to put here. So I'll put one here, 4. Okay. Now here, how many options? 10. Anything I want, right? Here, options, 10, right? So I have, for each digit, I have 10 options, and each one of them represents some power of 10, doesn't it? Right? This represents some power of 10. This is how many 10 to the zeros I have. This is how many 10 to the ones I have. This is how many 10 to the twos I have, right? Okay. So base 10, my question was, why is the log base, why is log base 10, why is that so important? Because base 10 is our number system, right? The next question I have for you is, why base 10? Why not base 8? Could we have come up with our number system and made it base 8? Could we have used base 5? Could we have used base 20? We could have, right? Why did we choose to use base 10, do you think? It's the first. What we made up the numbers. We made up the numbers. See, think about this carefully, because that's a circular argument. Because we decided that we were going to have these things represent 10 different things, right?
Isn't it like the notches on the corners?
Even easier than that. You're right there.
Because you can't put double digits in there.
Because we have 10 frickin' fingers, right? We have 10 fingers.
Oh my God.
Right? We have 10 fingers. I promise, I would bet my life that on a different planet, if we had intelligent life and they had four digits on each hand, right, they would be base 8. I'd be willing to bet, right? And if they had 2 on each hand, I'd be willing to bet they're base 4, all right? Because it's natural for us to want to count our fingers, right? So for humans, counting this way makes sense, right? But for a computer does not understand this idea of 10 digits. Computers understand what?
Base 2.
Binary, base 2, but why binary? Why?
True, false.
True, false. Why true, false? You're almost there.
On, off.
On, off. All a computer knows is yes, there is an electrical signal. No, there is not. It's on, turn the light on, turn the light off. That's all a computer knows. It has 2 options. Yes or no, true or false, which we represent with 2 digits. They are 0 and 1. So in a binary system, not base 10, you can write out any number you want. Let's do a 3-digit number again. And here I have how many options? 2. 0 or 1, right? Okay, so I'm going to put here 1. Okay, here I can put either a 0 or 1. I'm going to put a 0. Here I'm going to put 1. Okay, there we go. Now, the question is, what do each of these represent? So how many choices did we have? 2. So these should just be powers of 2. So this starting with 2 to the 0. This is 2 to the 1, and this is 2 to the 2nd, right? Now, what is 2 to the 2nd? 4. What's 2 to the 1? And it's 2 to the 0 is 1, right? So this is telling me I have 1, 1, right? I have 1, 1. I have no 2s, and I have 1, 4. So this is really the number 5 in our number system. The binary number 101 translated into our system is the number 5. Binary is 2 options for each digit, and then each one of those is some power of 2. And you can actually have a decimal binary. You can go backwards. What would this be? But I only have 2 options, so 1 here, right? What is this? 2 to the negative 1, but what's that? 1 over 2, 1 half. That's how many halves I have. And then this? How many fourths I have, right? This would be 2 to the negative 2. That's how many fourths I have, and so on and so forth. Do y'all see the difference between base 2 binary versus base 10? Do y'all understand how base 10 naturally comes because we have 10 fingers? Have any of y'all watched that movie, what is it, The Martian, where the guy Matt Damon gets stuck on Mars, and he tries to communicate with people on Earth? He's trying to figure out how to do it, and he uses, do y'all know how he does it? He uses something called Not Morse, not quite.
It was like some long thing.
Hexadecimal. He uses hexadecimal. Do you know what hexadecimal means?
Base 6.
Base
6.
16.
16.
It's base 16.
Oh, wow. Oh,
It's
'cause
base
hex-
16.
It's hexagon?
Yeah. So base 16 means you have, for each digit, you have how many options?
16.
16. Which means you can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can't use 10 because 10 is actually made up of 2 digits, right? You can't use 10, so what do we use? A, then B, then C, then D, 13, 14, 15, 16. That's it. Okay?
What do you,
So I've gone down this rabbit hole now, all right?
oh, this is just a side note?
Oh, yeah, this is all side note. Yeah.
So then how would you,
Yeah, so let's write a number in base 16, all right? I'm going to write a number in base. Let's just stick with the 3-digit number. So I'm going to write the number 2AF. So the number FA2, what number is that to us in base 10? Well, how many choices do we have for each of these? There's 16 choices, which means each of these are powers of 16, starting with 16 to the 0, 16 to the 1, 16 to the 2. All right, I have 2, right? This would mean, oh, well, let me see what these are. This is 16. I mean, sorry. This is 1. This is 16, right? And this one is, what's 16 squared? 2. Wait, no.
256.
256. I don't know why I was thinking 289. 256? Yeah, 256. Okay. Yes?
Does that mean that there's 15 times 56?
Yeah, so I have 2 1s, right? I'm going to write this way. I have 2 1s plus A 16s. But what's A? A is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means I have 11 A's. I mean, sorry, not 11 A's, 11 16s, right? That makes sense?
Wait, explain that one real quick.
What?
Explain the 11 to 16 again.
Okay, the thing is we're running out of symbols,
Yeah.
right? So this is representing 1, 2, 3, I'm sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, wait, sorry, 10. I should have put 10. 10, 11, 12, 13, 14, 15. Am I missing one? Hold on.
10,
How many options? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 11, right?
because you count the zero as a.
So this is 11, not 10. Does that make sense?
Yeah, 11.
11
And then plus
plus what?
16.
16 16s. And whatever that is the number in base 10.
See, if I landed on Mars, I would have died.
Yeah. Anyways, the point is there's no restriction on your base. You can have base 2. You can't have base 1. Nothing would make sense, right? If you only have 1 digit to put, then it wouldn't make any sense. Because then it would be, all these would be powers of 1, wouldn't they? So each one of them is 1. All right, so but you can have base 2 and anything up, all right? Our computers are binary, so they're base 2. And since a computer is base 2, last thing, promise. Since our computers are base 2, everything that we do with computers has to do with powers of 2, right? And if you look at all the powers of 2, right? You should recognize these numbers when you're buying a phone or a computer, when they talk about memory or hard disk space. They say, oh, I want the phone with 256 gig, right? Why is it not 200 gig? Right? Why not? Well, because it's a computer. Everything there is binary. So everything is measured in powers of 2, which is why you're going to have 256 gig or 128 gig or 64 gig. Everything is binary. Okay, we are thoroughly off the tracks. Back on. So now we want to know what the derivatives of these functions are. Really, everything else was just algebra, right? Here, remember these functions? Oh yeah, we studied them, we messed with them. What are the derivatives of them? So the first one that I'm going to give you here is I'm just going to give you the result, all right? You're going to just take this on faith, because to prove this, I would need to use the limit definition, and y'all told me already to stay away from the limit definition, right? Y'all did? In other words, if I wanted to figure out what the derivative of this was using the limit definition, I'd have to do this good old-fashioned limit. H goes to 0, f of x plus h, so I'd have to figure out what's log base a of x plus h, and then minus f of x, which would be log base a of x, and then all over h, and then I'd have to figure out what that is. And that becomes a little bit problematic, even though I can use that property to split this, or can I? No, I can't. See, that's the problem. You can't split that. That's a plus in there, not multiplication. So we run into some issues. And there's ways to do it. There's ways around this. But to save us time that I've already wasted today, this is going to be the result. And this is on your formula sheets. All right? If you want to know what the derivative of log base a of x is, it's just 1 over x times natural log of a. Let me do a couple of examples. And I should mention, we're kind of back to our nice derivatives where we're not doing implicit. Okay, we're going to kind of pause the implicit and go back to just our standard nice, where they're explicit. I've solved for y. So y is solved for. I want us to find what is log base 4 of x. What's the derivative? And I'll put the formula over here off to the side. The derivative of log base a of x is 1 over x times natural log a, right? That's the formula. So for us here, the derivative will be, well, we have log base 4 of x, right? So according to that formula, it should just be 1 over x times the natural log of 4. And I'm done. Please remember that natural log of 4 is just a number, right? That's just a number. You can go on your calculator right now and you can figure out what natural log of 4 is. It's just some decimal, some number. So we have 1 over x times the natural log of 4. I'll give you another one. How about y is log base, I don't know, 7 of x. The derivative of that would be 1 over x times natural log of 7. Is that pretty straightforward? Okay, what about this one?